Good morning, everyone. Thank you very much for joining us for the second lecture section of this conference. I hope you are all ready to listen to our second speaker from University of Eindhoven. So I'm very happy to be here and to introduce Professor Angel Reinders, because we are in the era of we are more focusing and moving towards net zero energy era, and we are not we don't have only to the main challenge. Let's say the main challenge that we have today is not only to understand and decide how we produce green energy. But one of the most important challenges that we have today is to how we design energy system and how we integrate this energy system in our societies, in our city, in our buildings, and in general in our lives. So I'm very happy today to be here to give the stage to Professor Reinders, because she is an expert, a leading researcher and pioneer in the sustainable energy transition. She's a professor of design of sustainable energy system at the Department of Mechanical Engineering of Eindhoven at Eindhoven University of Technology. Her current interests range from building integrated photovoltaics to machine learning for the design of energy systems with large use of photovoltaics and general renewables. Among others, she's a fellow of the Royal Society of Arts. Yeah. She's also a co-founder of the IEEE Journal of Photovoltaics. And her groundbreaking research spans from the World Bank in Washington, also to Papua. So you visit a lot of institutions, a lot of universities. And she also has edited several books on this topic, including The Power of Design and Designing with Photovoltaics. So please join me to welcome Professor Angel Reinders, and please at the stage.
Oh. Yeah, thank you, Anna Maria, for this very nice introduction. I also like to thank Nevin and Henning for inviting me on behalf of the whole committee. So I was really surprised to receive an invitation. So I don't know this community, but then I looked you up on the website and I thought, yeah, maybe there's a connection between my research and what you're doing. So today I'm going to talk about design-driven research for the energy transition. So I'll give a little bit of update of the energy transition, where we stand, and then I'll go into the methods. So what does it actually mean to have a design-driven approach towards energy transition? I'll show several different design-driven approaches, and then I apply that to the case of photovoltaics, because that's the topic I'm most used to. And then I will, of course, conclude. Yeah, but first I'll tell where I come from. I come from TU Eindhoven, and I work in the Energy Technology and Fluid Dynamic group that consists of two different groups that, on the one hand, develop sustainable energy technologies and storage means, and the other hand, work on combustion and making combustion more energy efficient, because in the energy transition, you still have to deal with combustion. And all that is meant to balance the Dutch energy system, of course, and maybe also other energy systems abroad. Just a little update on the status of the energy transition, and then I rely on the International Energy Agency and all their beautiful reports. So actually, we're doing really well with the renewable energy transition, because renewables are growing and growing, and at the right you see, for instance, the growth of photovoltaics and wind, and at the left of all the renewable installed capacity, and it's like exponentially going up. And yeah, it's estimated that about 45% of all the electricity generation will be renewable by 2030. That's really soon, so that's okay. But you have to think about where the energy is used, and here also I rely on IEA graphs. Like you can see, the industry, transport, residential use, and also a little bit of commercial and public service and agricultural and non-specified demand are using the energy that's produced everywhere. And this is then both traditional energy and renewables. And I think a big trend that we see is the increase of electricity demand. And I want to show exactly there at the right, at the bar with a large purple share for 2025 to 2030. You can see there is a really big increase in electricity demand for transportation, for buildings, and also data center, as well as heat pumps. So there's a lot of new developments that actually add to the issues in the energy transition. As I mentioned, electrification of transport is a big deal, and we see a strong emergence of electric car sales everywhere. So car sales for electric transport are growing 20% globally. That's really a lot, and that means also that a large share of the car stock worldwide will be electrically powered. So I will come back to that later. And then there's a last development, that's grid congestion, because with all the changes in the energy supply and the large share of renewables, in some countries even close to 95%, like in Norway, but also in Germany and Netherlands, we have a lot of renewables. You see that the balance between production and demand gets a bit out of the expected. And I show here two maps of the Netherlands showing grid congestion for consumption and for feed-in that I copied from the website of the grid operator a week ago. So these really recent maps. And what you can learn from this is that, it's actually hardly possible, because there's no white zones anymore, to connect renewable energy capacity. And also on many days, the grid operator has to do a lot of, let's say, special grid management to be able to supply the electricity that is required for industry and housing. Okay, so renewable energy transition is happening, and that also means that there's a lot of changes. And actually, I wonder then, in my research, what can we do to develop sustainable energy solutions that match with these trends that I just showed, and help to mitigate CO2 emissions, because despite all the renewable energy transition, we still have an upgoing trend of CO2 emissions, evidenced by measurements in Mauna Loa in Hawaii. And I thought a lot about this, and I think about 12 years ago, I thought about another solution than just technology development. So I thought, sustainable energy is something we're going to need anyhow in the future, because you don't want to compromise future generations by the activities that we undertake now. That's according to Brundtland report that was published in the 80s. But then, if you want to achieve that, then maybe you have to also consider how you change our environment and our system and our society in such a way that also serves our needs. And that can be done by a discipline called design. So, to my opinion, if you add sustainable energy with the discipline of design, you can really enable a long-term structural transformation of society, which is mainly based on renewables, the sustainable energy transition. And this is, of course, related. Now, we all know what's renewable energy. Sustainable energy is energy that's derived from a natural process that actually results in lower CO2 emissions than the traditional fossil fuel combustion systems at a factor of 10 to 20 less. So I won't say that much about this slide, but the next slide is about what is actually then design. And the discipline of design has a definition given by the World Design Organization that I show here. And it actually is a bit broader than you usually assume, because most of you assume that design is about making products, like for instance a chair or a table, but it's actually a strategic problem-solving process that drives innovation and builds business and leads to a better quality of life through innovative products, systems, services, and experiences. So it's much broader than just creating a chair and making it and using it. And actually means that those who can design, they have a transdisciplinary profession that harnesses creativity to resolve problems and co-create solutions with the intent to making products, systems, and services, etc. And usually it's indicated by a circular design process in which experience with existing properties of a current situation are evaluated by reflection. So you can conclude, for instance, using the example of a chair, this chair doesn't match the color scheme of my interior. That's a really important finding. It's also a value judgment. And then you analyze that, and then you compare different colors for the chair, and then recolor the chair. So you redesign it. So you create a new solution from the synthesis. And that actually can be put in practice again. So then maybe instead of a red chair, you have a green chair, put it in a new situation, and then maybe you're happy with it for half a year, but then thereafter you think, maybe you have to change it again. Maybe I don't need a chair, maybe I need a couch. So you go to design a couch. So that's a simple example to explain how this process works, but you can apply it to everything. You can apply it to wind turbines, and you can apply it also to policies, of course. You can also change policies in this way. Policies required to support sustainable energy transition. So the energy transition is not really a product problem, it's actually a societal system redesign that we actually have to go through. And for that change, we have to create new products, services, and processes. And that's really well represented by these 4 design levels by Jones and Van Eel from University of Antwerp, where identity and artifacts are the first reason to design something, but that also can be seen in the context of products and services, in the organization processes, and then the systems and policies. And this can also be represented in more detail by more complex overview, but also here you see the 4 levels. And then in every level you see the experience, the reflection, analysis, and synthesis. So it's all circular and it connects to each other at different levels. Okay, I won't bother you too much with all the details of all these methods, because as many of those, I just showed 2 of them. I would like to show what I did in this domain, and it's of course a very modest contribution, so I'm not going to say this is the final answer, but I just show what I've been doing in the past 20 years. And I will show some really old-fashioned slides from the year 2014. I just guarantee nothing has been made with AI, it's totally human. All the illustrations are human-made. Yeah, so I had a really tense hand at a certain moment when making the slides. So I want to tell something about the 3-layer model that could help with the energy transition, experiences I gained with an approach called Source of Innovation, and then also I will show what you can do with the Innovation Flower. And the 3-layer model, maybe some of you know it. It's a model for sustainable energy environments that was offered in the ERANET program. So if you ever had an ERANET project, you probably have seen this. And this actually is a model that says you have to combine markets with energy technologies and stakeholders in such a way that you can approach problems in the sustainable energy environment really well. And that was a model you worked in a project on smart energy systems in the Netherlands and Austria. Very nice project. And this resulted in all sort of solutions in better managing energy systems or in providing more renewables or integrating renewables in sinks. So these are some examples, but the list is not complete, so I could show 20 slides. But, just made a selection. So for instance, at the left you see Cube. That's a sort of home energy management product that can help consumers to make the right choices with use of the appliances and the use of the energy system. And it gives also feedback when they make a choice, then they can actually look at the Cube and get a feedback. At left bottom you see Bodhi. It's a smart home energy system also designed by students to give feedback on their energy consumption in an intuitive way by the color of the circle. So it shows where they have to reduce their energy consumption or increase it by the color. Then at the right you see a solar-powered electric bike that can also be charged by a solar charging station. And at the right bottom, a home that was designed for TU Delft in Green Energy Village, which is powered by PV, and it also can produce hydrogen. And you see there a hydrogen car that we bought in the project, but we also designed hydrogen scooters, and they could be powered every day by this system. So it was really fun. And besides that, we also did a lot of data analysis, and we looked at, for instance, electricity consumption in different smart grid pilots, and now you get all these graphs. But of course, in the end, you want to do something with the 3-layer model, and we put that in the perspective of design cycle. So, for instance, you see the cycle around it, which consists of a need, for instance, saving energy. That results in a design brief, like, for instance, design a home energy management system that can help to reduce energy consumption. That results in conceptual designs, products. If the products are great, they will be manufactured, they will be sold, and they will be used. And then again, you get from the experience a new idea on improvement. So that fits in the scheme of the user stakeholders that have needs, in the scheme of the technologies that are actually embedded in the products. So either a home energy management system or a hydrogen-powered scooter. And then they actually put in the market, that's logistics and sales. And so it means actually if you want to work on good energy products and services for the energy transition, then you have to also consider economic feasibility, technical feasibility, and usability and acceptance. Well, sounds quite logical, but do you ever experience the 3 different layers in one single project that you execute for the research? Now, besides that, I was also really heavily engaged in education, because I worked at University of Twente and also at TU Delft in the study programs of industrial design engineering. So I had to teach design courses, which I really liked, because actually before becoming an energy researcher, I was also in art school. So I thought that's really great. I can combine my creativity and artistic interest in my daily work. So I was really happy to do this. So I was very enthusiastic. I set up a master course called Source of Innovation, in which the design process were supported by various innovation methods to innovate better in the design process. And then I sort of, I don't want to say abuse the students, but I use the students to develop energy solutions, because that would also then fit to the research that was executed in my group. And we wrote many papers about it. So you can find a lot of papers on how to innovate with photovoltaics, how to innovate with sustainable lighting products, or how to innovate with fuel cells, because they resulted from this sort of educational projects. So every year we had about 30 to 40 conceptual designs originating from the course. And in the end, I also wrote a book about it called The Power of Design, that presents all the methods and some cases. And you see here a design process in a linear way, just to make it easier to understand. So you have a task, specification, concept development, preliminary layout, and then selection of the definitive layout that will be documented for manufacturing, and that's actually the solution. And around that you see all sort of names of methods and abbreviations. I won't go into detail with all the methods, because then I could speak a whole series of lectures. But I will just go through the topics that we dealt with to give you an idea what we have been doing. So this is one of the so-called outdated slides. So we started in 2006 with a project on hydrogen. Then we worked on solar cells, LEDs and PV, combined technologies in a project called Sustainable Highway. We worked on concentrating solar power, smart grid, luminescent materials, hydrogen. And thereafter, after 2019, I only worked on solar technologies, to be honest. So I thought it was not necessary to extend this table. But this sort of designs resulted from the course, like really fancy transport means, like for instance this rickshaw, which is powered by hydrogen. Solutions for PV-powered hydrogen refueling stations with nice maquettes. So it was really lovely to evaluate this sort of projects. It's all these nice tiny things that the students created. Concentrating solar power as lighting products for terraces. And also you can make tables that are self-powered by luminescent materials. You can charge your phone on it. And also really nice conceptual designs of PV-powered electric vehicles. And at the right you see some examples of the ideation process. Of course there's many more steps, but I could spend only one slide to this. And the resulting design is a bus that can actually power itself by extension of solar panels when it's in a parking mode. And this was designed in 2019, but I have to say, recently I saw somewhere in the news a serious commercial product that has this design. So the ideas that the students generated several years ago also find their way nowadays to reality, and that's quite interesting. Okay, now from all this, at a certain point I thought, what can we learn from this sort of approaches? So then I developed the innovation flower, which is based on interdisciplinary design perspective. And I show the innovation flower in the context of photovoltaics because it's easier for me to explain it. But the innovation flower is actually an interdisciplinary map with flower petals that each represent factors that are important for the design of a product that contains a certain energy technology, with the assumption that these 5 aspects are also important for any commercial other product in the market. So you always have to cover these 5 aspects to develop something that will be sold and used. And these aspects are technologies. So you want to have right materials, you want to have certain performance, you want to comply with standards. The other aspect is financial aspects, like something must be produced at a reasonable price. In case of energy systems, LCOE must be a good match with competitive alternatives, and there must be business models. Then you have a societal context, like the policy that drives, for instance, the energy transition and CO2 reduction, regulations, law, environmental laws, also communities that can connect to new developments. And these 3 aspects have been applied a lot to all sorts of energy technologies, but the 2 others have been omitted for a while. And these are human factors, and that's actually the factors related to use and interaction with things, perception, adoption, and emotions, going with the use or perception of objects, and design and styling. And design and styling is actually form giving, the use of shapes, color, and tactility for aesthetic appeal, for giving meaning to things, and also to connect to lifestyles. And here, in this slide, you see several examples of designs of solar-powered things. So either a window, a bicycle shed, a BIPV system in a villa in the Netherlands, Stella Terra, a PV-powered car from my university made by a student team, and a solar-powered chandelier. And they all match these 5 criteria. So technologies work, they can be made at a reasonable cost, except for the chandelier, because as an art object, that's the exception. They actually meant to reduce CO2 emissions, they have nice design and styling, and they have, actually in the design process, the human factors have been taken into account. Now, I show this for solar technologies. You can also, I did a little exercise yesterday evening because only solar, that's a bit, too monodisciplinary. So I made a slide for wind turbines. So you see here at the right, wind turbines that have, complied with the requirements for good technology and probably also for good financial aspects. But then if you want to embed better societal context, then in some cases you might like to consider wind parks on sea. But then human factors and design styling are not really embedded in those examples. But at the left, I show the wind tree that was made for COP21 in 2016. That has a really nice design and styling. And it's a wind turbine with many mini wind turbines in it. It looks like a tree. And there to avoid not in my backyard responses to wind parks, which is very common for humans, to not like that the wind park is being installed next to your home and you have to look at the wind turbines. So a company in Spain, Vortex, has developed bladeless wind turbines. So they look like poles without the blades, and that looks more quiet, I think. And I can look at that without getting nervous. Okay, now some additional information on design. So I'm going to focus on photovoltaics only because then I can go in more detail. But just for you in this meeting hall, if you want to apply to your own energy technology, please feel welcome to do so and do this exercise also when you get back home. But it's always possible to add design features to technology. Like for instance, for photovoltaics, you can add color, you can create curvature, you can add bendability, flexibility, you can create transparency, you can pattern by prints, you can apply 2D shapes, 3D shapes, you can make them lightweight, you can make them more sustainable by the right materials, you can make them stretchable. That's all possible if you want to do so. And in the PV sector, many people are working on this. And to help myself a little bit to figure out what's going on, I made a table for my book, The Power of Design, and also for designing with photovoltaics. Put all the PV technologies that exist, ranging from cadmium telluride to amorphous silicon to crystalline silicon, and then compare their typical sizes, whether you can pattern them, whether you can change their shape, whether they're flexible, whether they can be colored, whether they can be made transparent, and put that in the table. And just to help engineers and designers to make selections. Of course, these sort of features are changing the whole time. So maybe there's now new technology to have other features. But what we see in practice there at the right is all sort of colored PV application buildings nowadays. And they can be made in terracotta color, they can be made transparent, they can be made blue, they can be made in sort of glitter structure like at the right side there in Copenhagen. So there's all sort of possibilities. And it also requires that if you have these design features and you want to improve the design of energy products, buildings, and automotive application, they have to work with multiple stakeholders. Because besides the PV sector in this case, also other sectors contribute to the development of these components. And I will show that in the next slide. So this requires interaction with new stakeholders in other sectors than the energy sector. And that's also necessary because you have to homologate the new solutions, because anything that's been designed and put in the market must get official approval or certification by certain authorities, different for the building sector than for the automotive sector, to let a product be allowed on the market, ensuring that it meets safety and technical and environmental standards. And I'll show the next stakeholders on the next slide. So for instance, if you look at building integrated photovoltaics, then in red you see the regular stakeholders that actually collaborate with the PV sector or come into the PV sector in this sort of projects. So for instance, you have PV module manufacturers. You have legislative bodies that work, for instance, on building codes to make sure that any energy technology in the building actually meets the building codes as is common for all the building materials. And you have policymakers that want to, for instance, create net zero energy buildings. And they develop laws that actually help to further integrate and implement renewables. But also we have building owners. Usually they don't know that much about solar technologies or energy technologies in general. and they have to go through a learning cycle. You have construction engineers, you have architects, and also banks and financial services that have to fund this sort of projects. If you talk, for instance, about commercial buildings, those are big investments. So all these stakeholders have to work together, and that's really a challenge. And the same for PV integrated in cars. It's called vehicle integrated PV. So we have here module manufacturers, legislative bodies, policymakers, consumers, PV cell manufacturers, but also automotive designers and automotive manufacturers. So the automotive designer, he or she wants to create a car with good aerodynamics, but also needs to integrate the new solar technology. It's a big challenge for this person. And the same for the automotive manufacturers. They have to manufacture a component that's actually energy component. Do they want to manufacture that themselves, or do they want to buy it in? At least they have to include it in design in the manufacturing process. So it means also changes in the manufacturing line. And then coming back to more traditional approach, PV and grids. Also here we can see this sort of complications, because also here multiple stakeholders have to collaborate. Not just the PV module manufacturers, the legislative bodies and policymakers, but also the solar park managers, the electrical engineers, the banks that invest in solar parks, and also the DSOs and TSOs. They also have to deal with this. So they have to develop a common language and a common understanding. You don't see each other anymore as enemies, like the DSO doesn't need to see the solar park as an extra factor that contributes to grid congestion. We can also think it helps to make the grid more renewable. These sort of issues are really interesting. And yeah, challenge for all of us, I think. Okay, I have another set of slides left on building integrated PV. I will go through them really quickly just to show some features that are related to design and the specifics if you think about PV in buildings. But I'll go through it really quickly, and there's also a paper that you can read afterwards if you find it super interesting, and I show the paper and the link on the last slide. So for building integrated photovoltaics, there is many places in a building where you can apply PV in canopies, roofs, curtain walls, awnings, facades, also on walkable floors, balconies. So there's many options to apply them. Then I think it's for a designer really important to be aware that there's different approaches. For instance, you can design iconic buildings, like really grand design, like a football stadium or a university or school, and replicable buildings, like for instance, just a residential home or a holiday cottage that can be replicated multiple times. And for these applications, you have also different module types, like standard PV modules that are just blue or black, or dedicated BIPV modules that can be colored or transparent and have special features. Like, for instance, also features related to the building design. And that makes it also really interesting, because you see a historical timeline here of BIPV projects that starts from the 1970s. And the first solar home in the US looked quite technical. It's like, a system integrated in a roof with a lot of aluminium bars. I don't think it looks very beautiful, but it worked quite well. And what you see then until the year 2000 is a lot of square, rectangular design with a lot of greenhouse gas, of greenhouse-like construction parts. But thereafter something changes and you see more color. You see shapes, like for instance in La Scène musical in Paris. Also prints on facades, like on the solar facade of Soltec. And also even solutions for heritage buildings that are indistinguishable from traditional building materials. It's super interesting, of course, for energy production. Here are some daily power productions shown for different sides of the building, on the west, south, east, and north, and at an optimally oriented roof. There can be issues, and any design has to take into account issues with shading, also thermal and other stresses, wind stresses, snow loads. It's all relevant for this sort of designs, and it goes actually beyond the common energy application. Now, of course, you have to take into account cost. And what I find really interesting about these graphs is that for different parts of the building, like skylights or rain screens or roof tiles, you have a different price range. It's going from something like 80 euro per square meter up to 700. But in the lower price range, this is competitive with conventional PV. So even if there are some objections against this from a cost perspective, I would like to say that's not true, because this is already feasible from a financial perspective. Skip this one, and then if we look at CO2 emissions, then often it's mentioned that, for instance, in the design of building integrated PV, CO2 emissions will be too low, but you can see there at the right the emissions of the electricity mix in Europe for different countries. So it's quite high. And then you see at the left for all sort of orientations of PV in building parts, like for instance an optimal orientation for flat roof, 90 degrees south, west and north, that in most cases then also CO2 emissions are lower. So there's always CO2 reduction possible in this case. In which country you live? Well, not in Norway, of course, because there you have a lot of hydrogen power, but let's say in 90% of the European countries. Okay, color PV, I showed this illustration already, but I come back to it because if you want to color solar technologies, you have to add either coatings or colored glass or colored encapsulant, and that reduces the power output, of course, because light will be less likely to reach solar cells. But if you make wise selections, then this power reduction can be limited to something like 20%. That's great, because as you saw, the CO2 emissions are very low, and also the costs were very low, so this is not going to affect dramatically the overall performance of this sort of applications. And then to come back to the societal aspects, there's a lot of barriers, of course, to this sort of new developments. Technical, legal, societal and economic barriers. And this scheme shows that there is barriers perceived, but there's also barriers that can be overcome, like, for instance, aspects related to product availability or lack of expertise. So I think also in this domain, making this more accessible for everybody, we have to work on training and also work on standardization and create awareness about the real cost and the real CO2 emissions and the real performance in with regard to efficiency, because there are a lot of myths that doesn't work. Okay, that's why there's also a lot of policy and regulations from the European Commission that help to support this sort of design approaches for PV, like we have an EU solar standard, regulations for nearly zero energy buildings, that's compulsory for all new buildings. There's a European Solar Charter, there's new European Bauhaus, new Zero Industry Act, and all that helps to support this energy transition. And also, what we do, we develop design guidelines. And this is an example of a design guideline developed by one of my PhD students. She also works in Florence, so it's like a collaborative project with Italy. And we worked on a design framework that can help both architects, construction engineers, organizations from the financial sector, but also organizations related and people related to city management to better guide the design of PV systems in buildings. And the innovation flower that I just showed serves as a background in this process. And this will soon be published, so it's on its way. And then I can also share the full method. But I want to show here that also here you have this situation that you have a strategy, then also analysis, selection, and then adaptation, like in a real design cycle, but then structured in a framework that can be understood hopefully by many different stakeholders. I'm just going to wrap up now, because also see I'm at the end of my speaking time. So all this is now being applied in a project that I'm engaged in with 4 technical universities in the Netherlands. It's called the Heritage Program. And this is about the issue of urban overheating. So it's a project on how to prevent that citizens living in aging built environments suffer from heat under climatic changes. And what we want to do in this project is we want to develop new design solutions. Of course, we want to conduct research, and we also want to develop a warning system. And in this project, we have many research questions, but just want to emphasize that besides all the questions you have about remote sensing and how the water bodies contribute to cooling, and also how we can reduce the heat flux incoming to the city, we specifically work on energy solutions with solar energy technologies in the redesign of buildings and neighborhoods. And I think this sort of approaches, this design-driven approach with different researchers with different disciplines as a background, really can help to develop solutions that find their way in a system change that we need for the energy transition. Okay, I end up with a few examples of solar-powered electric vehicles, because that was also a topic I worked on the past 10 years. And there's 2 possible solutions in making electric transport more sustainable if you use solar power. So one is to use solar charging stations, and the other one is to integrate photovoltaics in car bodies. And these examples were investigated in my group. And the main reason to do so is in particular because the emissions of PV systems of just 30 grams CO2 equivalent per kilowatt hour are way lower than the emissions of the grid in the Netherlands, and also the European grid, in particular also the grid in some Eastern European countries. And also because if you think about how much power you can produce by PV modules, and you compare that to the drive range of a vehicle, then it's really possible to drive solar in the Netherlands with an irradiation of 1,000 kilowatt hours per square meter, because you can actually gain 4,000 kilometers per year by producing solar electricity for your electric car. And it becomes even better if you go to places like, I think, south of Italy, north of Africa, Australia. There you can drive 10,000 kilometers per year on solar power. So it's really interesting. So what we did in my group, we developed, of course, models and tried to be interdisciplinary. So we modeled this in a technical way, in an economic way, and in an environmental way, and compared solar charging of electric cars with also a little bit of charging by the grid for difficult months in the year. In the Netherlands, for instance, then we don't have any solar power. We compared that with grid-powered electric vehicles and gasoline-fueled cars. And then we found out that for different countries like Netherlands, Norway, Brazil, and Australia, you get different results. But for most of the countries, with a very small array of about, let's say, 2 kilowatt peak, up to 3 kilowatt peak, you can charge your electric car over the whole year. This didn't work for Norway, because in Norway a lot of power is produced by hydro, and that is much more competitive than PV, but it's one of the few countries in Europe, and most of the countries don't have hydropower. And also here at the right side you see a graph in which the CO2 emission is shown, and you see then in the gray bar if you charge an electric car by the grid, and in the yellow bar if you charge it with 100% PV power, and all the other colors are in between. So you see PV power really results in lower CO2 emissions. So knowing this, there was quite some developments in via PV, like vehicle integrated PV, starting from cars for the solar challenge that are racing cars, to cars made by manufacturers like Audi, Sono, Toyota is working on it, Lightyear, a Dutch company, And also Nissan and Hyundai are really working on this sort of solutions. And here we see already first commercial applications in the market. It's really great. But there's some issues with the design, and a lot of research is being conducted now in Japan, also Netherlands and Germany, on getting PV cells into body parts of cars, and then you have to distinguish between roof integration and hood and side integration. And the funny thing is that for both parts of the car, you have different design requirements. So it makes it extra complicated, but you see advances, and for roof integration, you need curved PV, you must be oriented towards the sun, it must be very rigid, impact-proof, it must be stable, and that means also that if you add it to the sides of a car, it must be pedestrian safe, and therefore also preferably glass-free, because you don't want to have impact and then hurt people with a lot of glass. So all this being developed at the moment, so there's no final solution, but I showed 2 examples of cars that have or had PV in their body parts, and I think it looks just great. I mean, I could drive with such a car. Okay, so now we come to the conclusions. It was a very long talk, I'm aware of it. Sorry for long talking, but I hope I convinced you, not by talking long, but also really by the content, that to enhance the energy transition, you have to better integrate sustainable energy in products, buildings, and cars, and other things. But then you have to apply design approaches. And that means that you have to engage other stakeholders than just the researchers or the designers or the engineers. And you have to think about advanced or enhanced design features for energy technologies. So I think that's the message I want to convey for now. And I also have 2 recommendations. I would like to ask you maybe to try once, maybe twice, to apply design-driven approaches in your own projects to see what it yields and whether you get other insights. And I think also, to make this work better, we have to develop new methods, especially at the level of system design for the energy sector in collaboration with stakeholders, and really redesign our energy transition. So, this is another slide. So if you want to do this, you can use the method, and you can also maybe read my books. It's not an advertisement, but the methods are really well described in the books. And I would like to acknowledge many people, like all the students who contribute to design projects and all the collaborators in the various projects that were represented in the slides. And I would like to thank you for your attention.
Thank you for this inspiring presentation. I'm really a supporter of the design-driven approach. I also always believe that beauty has a very huge impact on the social acceptance of technology in general, especially in case of renewable. Let's see if we have some questions from the audience. I see several hands. We have just 7 minutes, so I suggest you to be very short in your question. Thank you. Okay, let's start with Professor Sikri.
Thank you. Thank you for a very insightful presentation.
Thank you.
This is Bilal Kılkış from Austin Technical University. My question is about, in line with the design approach, did you or are you going to consider solar PVT systems, innovative systems, as part of providing not only electric power but also heat, which according to my research in collaboration with the TU Delft Solar Village, it is feasible, at least environmental feasible, up to Delft or up to even Amsterdam to use PVT panels, which may be also used for greenhouse applications. Thank you.
Yeah, I fully agree with this suggestion. Also in our group we work on this. So I fully agree with you that PVT can help also to mitigate heat. And it, maybe we can discuss later on, but in our group we work now also on curved PVT to see how the design of PVT can be better integrated in buildings with other shapes than just a flat PVT. But there's always this complication between connecting electricity with water systems, so it's challenging. And I think that's a barrier here, but maybe with improved design it becomes easier to install it also. Yeah.
I have many questions, but I will start with the most consequential one about design. We can see from Elon Musk how to redesign the car completely, scratching all the business model that existed before. And we also can see how European industry is completely unable to redesign its business processes, which are built on servicing cars, very high labor behind the car industry, which is completely incompatible with the cars of future. So what do we do in those cases? It's a very disruptive one, very consequential one.
Yeah, I agree with your comment, and logically, this sort of technical innovations, like for instance solar-powered cars, they actually mainly put in the market at the moment by Asian car manufacturers that have, let's say, the possibility to more easily innovate their production lines and have also different business models. But yeah, indeed, I agree with you that at the European level, we have to somehow stimulate industry to make either better energy technologies and really produce them in such a way that they're competitive in the market with other countries or other continents, or maybe create new types of industry. But I'm not in the European Committee. But that's something that has to be done, I agree. Yeah. Otherwise we're going to lag behind. But it's a very different topic for discussion. Yeah.
Thank you for your question. Please.
Hello, thank you very much for the interesting models. My name is Abdul Mohammed Gholamzadeh Chofre. I am associate professor in project management at Birmingham City University. In 2021, I and my co-authors published a paper. It was about, in RSER journal, it was about strategic management for global energy. And in there we introduced two environments, which was internal and external environment. In external environment, we mentioned that there are like competitors and also 5 forces of Michael Porter, which are like bargaining power of suppliers, bargaining power of customers and the rest. And I feel these are missing. And why I say this is important, because for example, when we are talking about materials and suppliers, this is very important to know about. Now nations are competing about this and supplying about this. For example, we can see China, Europe, and US, they are competing for this rare material and rare elements. I think it would be good in the models we think about this. Otherwise, in future, we face to this problem of supply and also competition. Thank you very much.
Yeah, thank you too. I mean, I fully agree with what you suggest, and I think also with my last recommendation to work out the methods and make them better matched with the situation in the energy sector. Something like rare materials should be included in maybe the topic of societal aspects. Yeah, fully agree. Yeah.
Thank you very much. I don't know if you have more time. I have 2 questions. Just one moment. Okay, Professor Wang.
Thank you very much for your presentation. Actually, with the fast development of PV integrated to the power grid, the output power is variable, is stochastic, depend on the solar irradiation. So that would be a big problem, especially for those kind of small scale, small capacity integrated to the distribution level, not on the, the high voltage level. So it's big capacity solar PV station. So do you have some kind of comments about how to handle those kind of stochastic output power to balance the output and the load? Thank you.
Yeah, that's a very good question. And at the moment, I think majority of the PV sector thinks about storage as a solution. So there's a lot of storage solutions that are being developed at the moment. And yeah, previously, before there was this grid congestion issue, then of course you could feed in solar power any moment you want to feed in. But now you see a lot of curtailment, of course. That's known. But I think what you suggest is, of course, an interesting topic, but that is, like say, how should I say this? This is a technical issue, eh? Yeah, technical. Also a bit an economic issue, of course, because if you have a solar park and you can't feed in because of the stochastic power production and imbalance with the congested grid, then you lose also part of your investment. But do you want to hear about the technical solution, or how this fits into the design-driven approach? Okay, the approach, yeah. Yeah, so then in that situation, you should look together, not just you as the problem owner, but with the TSOs and DSOs and maybe storage system developer and consumers also at this problem, and see how you can solve it while complying with the 5 aspects, like technical, financial, societal, human factors. Maybe design and styling doesn't matter that much, but just in case you would end up with a solution in which storage would be integrated at the neighborhood level and you would have a big battery somewhere, then maybe design and styling of the battery container would be also part of the project, because nobody will accept a big cubic block in their neighborhood. At least that's the stories I hear now in the Netherlands. Yeah, so maybe do some co-creation or so.
Thank you. The very last 2 questions, because we are going for the lunchtime.
Elham Ramin from Technical University of Denmark. A very interesting talk. Quickly, you mentioned this framework of design and redesign, the iterative process.
Yeah.
How would it promote the circularity in design? Because what would you do with the old models? Like from the green chair to the red might be easy to just paint on it, right? But then from the red to the sofa, would you throw away all the chairs you produced to make
Yeah, okay. So I gave that example to be able to explain really quickly the basic circular design process. But then, of course, I did not mention that as circular design process in circularity in the sense of sustainable circularity, because that is then a level higher, that you also have all the R's like reuse and recycle, and anyway, that can also then be embedded, of course, but we're not yet in the stage that we think as designers. So that's why I did not address the circular design process as the sustainable circular design process. But I think for the most people here in this meeting hall, you conduct research from a research perspective, and what I want to address with my talk is the fact that you can think as a designer and then touch different topics that also can contribute to a solution. But I fully agree that next step would be then circularity. Yeah, 100%.
So many thanks, Professor. This is Albana Kona from European Commission Joint Research Center. Just to link a little bit the dots of what Professor Dewich said before, what is missing in Europe? So I have published 3 years ago a report of identifying what is missing in Europe between research and innovation. So why we have a very big, let's say the largest infrastructure research finance projects, but still we have a lack on uptaking this research into innovation. So for that, for the time being, the Commissioner on Research just launched the project of opening joint research center, top-notch laboratories for startup initiatives. So this is an invitation also, please to take and come to JRC and use our infrastructures in order to scale up from research to innovation. Then my questions to you, sorry, I made a little bit of publicity of our institute. How do you see TU for Heritage coming? This is a wonderful initiative, so you are clustering technical universities in the Netherlands for heritage. And how do you see this to go into a startup, to an innovation company? Do you see your students tomorrow to be a to create business on this idea?
Yeah, yeah. Well, it's not the aim of the project. The aim of the project is to come with design solutions, and also to develop models. So that's what we got paid for. But yeah, I see now already possibilities for new business and services. Like, for instance, the problem is, of course, with aging built environment, that not many people can easily calculate what's the effect of new technologies on their indoor thermal comfort or their energy self-consumption potential. So what we do now in our group, we work on simulation models to better assess and quantify what's the effect of, for instance, PV in combination with cooling techniques, in combination with demand-side management. And then when that's ready, then I can imagine that one of my PhD students that developed that simulation tool, that he or she starts a consultancy. Yeah. And then helps many others to renovate their heritage buildings, because I say heritage, yeah, we calculate heritage until the 80s, so it's a very long stretch. So we don't talk about 17th century buildings, but all the old buildings until the 80s. Yeah, and then you can really have a business. Yeah.
Thank you very much. I think that we are a little bit late, so I would just would like to thank you again, Professor Reinders. And I want to make sure that you check your schedule for the social program, so be in time for the bus and for the locate the point where we have to leave. Thank you very much again, and we will follow, keep the discussion later. Maybe.